It's time to look at the product rule. So we have two functions, and right now I'm going to give an explicit example. We're going to get away from that pretty soon. Let's say we have f of t is t squared, g of t is sine t. We know the derivatives of those individual functions. This gives 2t, this gives cosine t. Maybe that will let us apply some sort of rule that will calculate the derivative of t squared sine t. So we could write it this way using the names of the functions. We could write it this way, and that avoids naming the functions. Well, and I'm using t because below I'm going to really think about this as with time as the independent variable. Here's the thing: if people guess this, they often will guess that it's the product of the derivatives. Well, it's just not true that the derivative of a product is the product of the derivatives. So that's really important. Wish I could spend more time on that, but it's really important that that guess is wrong. Now, to think about this, it's actually wonderful because we don't have to really worry about exactly what f is and what g is. We just have to think that f is something that takes t, say time, and produces some quantity. And derivatives are all about small changes. What happens when we wiggle t, and what happens to the output of f. What happens when we wiggle t, what happens to the output of g. That's what those derivatives predict. And then what we really want is what happens to the output of f times g. So the key is really the connection between what value f is giving us. So I'm going to call that w because we're going to make it the width of a rectangle, as you see on the right. And the output of g, we're going to make that the height of a rectangle. And all we really need to understand is how the product of those two quantities changes based on how the individual quantities change. And the picture is really, really nice for that because it shows us, it's geometrical, and it shows us that there's a key simplification we get in this case. So here's the question. We've changed it to a geometric question. How does the area of a rectangle, w times h, change when we change the sides by very small amounts? Remember, the technical definition here is we're going to take limits. I'm not going to actually phrase it in terms of limits, but I'm going to phrase it in terms of what if we change w and h by very, very small amounts? And if we see something that's simple when they're small, we can even make them smaller and smaller and smaller and smaller, as small as we want. And if something simple happens in that case, then that's going to give us the rule for the derivative. Okay, so let's look at the GeoGebra picture here. And the key thing, well, so let me just explain what's going on here. So I want to think of the blue rectangle as our home base. That's what happens before we change w and h. And then we're going to change w by a little bit, and we're going to call that dw, because that's our standard notation for changing a variable a little bit. We're going to change h, the height of the rectangle, by dh. So the new rectangle is all of a, e, q, f. But I've already got it colored in a certain way to emphasize what we really want is the change in the area. The blue isn't going away, so the change in the area is all three of the other pieces combined. And so we really just are interested in, if I wiggle w a little bit and we add on this little bit to w, the segment between b and e, here it has length 0.5, just to be definite, and we add on a little bit of segment df here, which has this length 0.6 in this example so far, then what is the total area that we're adding on? And the absolute key to what makes this argument work is that if dw and dh are very small, which piece can we ignore? And the question is, this little corner piece, does that matter much? So let's look at a few explicit examples of that. Okay, so here's the one I have written out. Here's the one I have written out, which is where we're changing, we had 5 and we changed it to 0.5. We had 3 and we changed it to 0.6. And so the total new area is the sum of all three of the new pieces, the pink, the green, and the brown. And so we got 1.5 plus 3.0 plus 0.3. So just a simple numerical calculation. Okay, but I want to suggest that this corner piece is not very significant. And we're going to see when we drive dw and dh to be smaller and smaller, I hope that'll be more convincing. So I'm going to just say, well, what would happen if we left out the corner? And that's just going to just be the 3 plus the 1.5. And I want to see exactly where that calculation comes from. That's very interesting. That is equal to, it's equal to the change in the width times the actual value of the height, because those are the dimensions of this rectangle, plus the change, plus, let's see, and I tend to write it in a certain way, plus the height itself, the width itself. I like to write it in this way for various reasons, times the change in the height. So the key thing is that we're pairing together a change in one variable with the actual value of the other variable. That gives us the area of the pink and the area of the green, and we're adding them up. And I still have to justify for you why it makes sense to just look at what I'm calling dA here. I claim that's going to be our idealized change in the area, and to ignore the corner. But remember, we don't really care when we're doing a calculus derivation. We don't really care what happens when dW is this huge, huge change, 0.5. By calculus standards, that's enormous. And 0.6, oh my God, why are we changing so much? We want to imagine that dW and dH are really infinitesimal changes, really, really super tiny. And we want to see if something simplifies in that case. So the 4.8 seems like it would be the right calculation here, but I claim the 4.5 is more on the right track. So I'm going to go and I pre-prepared a slightly different version of this. Okay, so now I've got something where I've cranked down. I'm not changing the original W and H here. Just to save time, I'm not going to do different versions of that. But now dW is just 0.1. Now I'm really not cranking it down that far, but I want it to actually be still visible on the screen. And dH, 0.05, is about as small as I can get and still actually have some sort of visible width there. Okay. BEPC is 0.3. DCRF, the top one, is 0.25. It's kind of showing up over here, but that's this green rectangle. And again, let me point out that that pink one is the change in W paired with the actual value of H plus the actual value of W paired with the change in H. That's individually the rectangle, the calculations for the area of those rectangles. It's exactly how that is calculated. A change in one variable matched with, multiplied by the actual value of the other, and then you add it, because just there's two pieces. Now, again, that would be not very correct if we can't have some argument that we can ignore this little tiny rectangle up here, CPQR, this brown, although you can't see the color anymore. But at this point, that is getting to be quite small, 0.005. And so we're really not off by much. I'm saying we should think of this as a good approximation is 0.55, and the real change in area here will be 555. Let's see what's happening here. We're taking two small quantities, medium small quantities, 0.1 and 0.05. Those medium small quantities go in as is to the dA. So you get a medium small quantity after all. But the extra, the stuff that I would like to ignore, is a small quantity times a small quantity. That is proportionally going to go away. When I drive dW and dH to 0, this guy, the CPQR, will go to 0 much faster, and in the end, we can neglect it. So I'm going to take consequences of that in the next part.